Here we go into some chapter 10 section 3 ideas. And so in section 3 we're dealing with means. So in section 2 we were dealing with proportions, section 3 we're dealing with means. So researchers wanted to measure the effect of alcohol on the development of hippocampal region in adolescence. The researchers randomly selected 13, so there's our sample size, with alcohol use disorders. They wanted to determine whether the hippocampal volumes in the alcoholic adolescents were less than normal volume of 9.02 centimeters cubed. So this is what it's believed to be, is 9.02 centimeters cubed. And so we're going to see if it's different. It's kind of what we're looking for. An analysis of the sample data revealed that the volume is approximately normal with the sample mean, that's a sample mean of 8.05, and a sample standard deviation of 0.8. Conduct an appropriate test at the alpha 0.05 level of significance. Whether the volume were less than normal. So they wanted to determine whether the volumes in the alcoholic adolescents were less than normal. So again, I said previously, we're dealing with mean, and this one's always going to be equal to our null hypothesis. Our alternative hypothesis is going to be less than, because they told me less than normal, right? So let's check that. Again, these numbers are always the same. This is what's believed to be true, the 9.02. And they gave us some clue. They said less than normal up here. And again, we know we were dealing with means, whereas in section 2 we're dealing with proportions. So then it says find the test statistic. Now the test statistic is something that we can find easily with StatCrunch. It's also going to find us our p-value. But I'm going to tell you it's an archaic thing. Most people look at p-values to determine this. So I am dealing with means, so I'm dealing with t-stats. I have one sample, and it has a summary. They give me my sample mean, my sample standard deviation. So let's fill all these numbers in. So my sample mean was 8.05, my sample standard deviation was 0.8, and my sample size was 13. Now again, the null was believed to be 9.02. And we said less than 9.02. And so once we get here, we can go ahead and compute, and it'll give us our test statistic. And I'll tell you kind of what that means, even though the main thing is to know a p-value. So our test statistic is negative 4.37. So let's go back here and say negative 4.37. And we get it correct. Yay, whatever that means. Find the p-value. That's the one that I'm a fan of, 0.0005. Oh, to 3 decimal places would be 1. So we just got to be careful about our rounding, as always. Excellent. And then it's going to say, what are we going to do? So I told you last time, if the p is low, the hoe got to go. Same scenario, right? Our p-value is less than our alpha. So our p-value is low, so the hoe got to go. We're going to reject the null hypothesis. So I'm going to reject the null, and there is not sufficient evidence or there is sufficient evidence. And so typically when we're rejecting, there is sufficient evidence to conclude that the volumes are less than normal. So we have sufficient evidence. Our data has said that it is less than the believed 9.02. Alright, so let's look at one more of these. Let's see how number 10 looks. 10 is a math teacher claims that she has developed a review course that increases the scores of students on the math portion of a college entrance exam. Wouldn't that be great? Based on data from the administrator of the exam, scores are normally distributed with a mean. So they believe that the mean is 512. The teacher obtains a random sample of 2,000 students, so a pretty large sample size, puts them through the review class and finds that the mean score of the 2,000 students is 519. So it is higher, but is it significantly higher? Every time we do a sample, we're going to get a different mean. But is it far away, enough away from 512 to say we really think the population mean has changed? So let's make sure we know that the mean equals 512. Let's see if there's anything that says that we think it should be greater than or not equal to. That increases the scores, right? So that's what's telling me that our alternatives is going to be greater than 512. And then it's going to ask for the test statistic, and then also it's going to ask for the p-value. So let's go back to our stat crunch. We know 519 with a standard deviation of 119. So let's do another t-stat. We could probably get away with doing a z, but because it's such a large sample size. But we're going to go with what we know. 2,000. I think the mean was 512, and we said it was going to be greater than the 512. I'm going to compute. There's my t-stat. I'll show you for real on this one what that means and how we get the same conclusions. So 2.63 is our test statistic. And let's check it. And then our p-value to 3 decimal places is 0.004. And my p is low. And so is the sample mean statistically significantly higher? And so it is, because it is lower. There's a small chance of this happening, right? We were comparing it. Our alpha, I think they said, was 0.10. Like the chance of this happening is 0.004. So 0.4% of the time will I collect a sample of 2,000 and get a mean higher than 519. All kinds of parts remaining. I do think that the mean score of 519 will affect the decision of a school administrators or admissions administrators. In other words, does the increase in the score have any practical significance? I would kind of say no. I'm going to get in trouble on this one because 519, 512 isn't a huge difference. It is statistically significant, but if you were looking at one person's score, I don't think they would think that would be significant. Sweet, they agree with me. So now we're just testing another one with 400 students, and we're seeing what the test statistic would be. So let's look back at our test statistic up here. 2.63, that is our test statistic. So I want to look in the book. They have a nice picture of kind of what's going on. We just had a one tail. We said it would be greater than the 512. So we have a one-tailed test. Here's a one-tailed to the left, a less than, and this is a not equal to. But our test statistic we got was 2.63. 2.63 was our test statistic. So when I'm looking is my test statistic in this shaded region? If it is, that means I reject the null hypothesis. Same thing as P low, ho, gotta go. Now this critical value, this T alpha, kind of just sets off, it is my divider between the non-rejection region and the rejection region. And the way we would find T alpha is we could use our calculator. So stat calculator T, and my degrees of freedom, since I had 2,000, would be 1,999. And I'm looking for that test statistic when I have 0.1 to the right. 0.10 is what they said alpha was. And so that is my divides my critical region. Right? That is a T alpha, 1.28. So here's 1.28. It breaks off my non-rejection region, and my rejection region. So that 1.28 we just found compared to the test statistic of 2.63, which is over here. So it is clearly in the rejection region. So that's why we would reject the null hypothesis. Or, as I like to say, P is low, the hoe gotta go.